Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating article about writing a simple driver in Rust. It's a game changer, really. The potential for safer, more efficient kernel-level code is huge.
Absolutely. I've been following Rust's progress in systems programming with great interest. This article highlights the challenges and triumphs of bridging the gap between Rust and the Windows kernel, right? What are the key hurdles mentioned?
Precisely. One major challenge is the verbosity involved in converting C types to Rust. The author cleverly suggests using wrappers and macros to mitigate this. But the core issue is interfacing with the Windows kernel APIs, which are predominantly C-based. It's not a trivial task.
I see. So how does the author approach building this driver? What tools and dependencies are involved?
The author uses the Windows Drivers RS project from Microsoft, which is essential. You'll need the Windows Driver Kit, WDK, or the Enterprise WDK, and LLVM with Clang. The project structure itself is a Rust library, built using Cargo, naturally. There's a crucial build.rs file to configure static linking to the C runtime library, CRT, which is a common pitfall in driver development.
And the cargo.tom wall file? What are the key dependencies there?
Oh, that's where the magic happens. The cargo.tom specifies several crucial WDK crates, WDK macros, WDK alloc, WDK panic, and WDK sys. These provide the necessary abstractions and low-level interoperability with the kernel. The author also cleverly uses a custom global allocator, WDK allocator, because the standard library isn't available in kernel space.
That's a really smart workaround. So how does the actual driver code look? What are the key functions?
The core is the driver entry function, the driver's entry point. It creates a device object, a symbolic link for easier access via create file, and sets up the major function handlers for IRPs, IO request packets. The author uses println, re-implemented to use dbgprint, which is a nice touch for debugging. There are handlers for IRPMJCREATE, IRPMJCLOSE, and the crucial IRPMJWRITE, which handles the thread priority modification.
And the IRPMJWRITE handler? That's where the real work happens, right? How does it manage thread priority changes?
Exactly. It receives thread ID and priority from a custom structure, thread data. It then uses pslookup thread by thread ID to find the thread object, and keyset priority thread to change its priority. Error handling is crucial here, and the author uses a loop with break statements for clean error handling. It's a very elegant solution.
The article also mentions signing the driver. Is that a straightforward process?
Not entirely. While the crates support signing with INF/INX files, this example doesn't use them, so manual signing with SigTool is necessary, using a WDK test certificate. The author points out a minor quirk. The output file is a DLL, not a SYS, which is a bit unusual.
Interesting. So what's the overall takeaway? Is writing kernel drivers in Rust practical?
Absolutely. The article demonstrates that it's not only possible, but also offers significant advantages in terms of safety and maintainability. While there are challenges, the Windows Drivers RS crates and the techniques shown in the article provide a solid foundation. The author rightly points out that more robust wrappers and improved crate support would make the process even smoother. But the future looks bright for Rust in kernel development.
I agree. This is a significant step forward. Thanks for this insightful discussion.
My pleasure. And to our listeners, thank you for tuning in to Tech Bytes and News. We hope you found this discussion informative and engaging. Have a great day, and we'll catch you next time.
Bye-bye.